one or two more. So the first speaker of this afternoon's session is Emily Stark from Technion. There's a title there, Commensurability, Classification of Certain Right-Angled Coxeter Groups and Related Surface Amalgams.
Okay, thank you. Thank you very much for the invitation. It's been a very good conference. So today I'll describe the commensurability classification of certain right-angled Coxeter groups and related surface amalgams. And this is joint work with Pallavi Dani and Ann Thomas. And I'll start with the definitions. So throughout the talk, suppose that G1 and G2 are finitely generated groups. We say that G1 and G2 are abstractly commensurable which I'll denote by the letters A and C if they contain finite index subgroups which are isomorphic. Any finitely generated group is quasi-isometric to any of its finite index subgroups. So if two groups are abstractly commensurable, if two finitely generated groups are abstractly commensurable, then the groups are quasi-isometric, and this leads to two natural problems in geometric group theory. One is, within a class of groups, can you identify the quasi-isometry and commensurability classes? And the second question is to determine for which classes of groups the converse holds. So we consider these problems for a class of right-angled Coxeter groups which I'll denote throughout the talk by the letter W. And to set notation, gamma will always be a finite simplicial graph. And W gamma is the right-angled Coxeter group with defining graph gamma, which has one generator for every vertex in the graph. Every generator has order 2, and two generators commute if and only if the vertices are contained in an edge of the graph. And we've seen many examples of these groups throughout the week, and one nice feature of this class of groups is often graph theoretic properties correspond to group theoretic and geometric properties. And we can define the class W as follows. Say a right-angled Coxeter group W gamma is in the class W if and only if the following conditions are satisfied. So first, we assume the group is delta hyperbolic. Mousselang showed this is equivalent to the fact that in gamma, every square has a chord. Meaning if you see a square in the defining graph, for gamma, as Jason explained yesterday, between some pair of opposite vertices, there must be an edge. We assume our group is one-ended. Or equivalently, as Mahalik showed, the graph gamma is connected and contains no separating complete subgraph. Which would give you a splitting of your group over a finite subgroup. We assume that the group W gamma is two-dimensional, meaning that the graph has no triangles. every right-angle Coxeter group acts on the Davis complex for the group, which is a cat-0 cube complex. And if the graph has no triangles, then the Davis complex is a square complex. That's what we mean by two-dimensional. We make one simplifying assumption, which is that the graph gamma is 3 convex, meaning that between any vertices of valence at least 3, every path must have length at least 3. This doesn't have a natural group theoretic analog, but it will make the rest of the results in the talk easier to state. For example, we also assume our group splits over a two-ended subgroup and under the above assumptions, it was shown by Mahalik and Chance that this is equivalent to the fact that the graph gamma has a pair of vertices which separate the graph into at least 2 components which contain at least 2 vertices each. And finally, we assume that the JSJ decomposition of W gamma contains only two-ended and maximal hanging Fuchsian vertex groups. Dani and Thomas show that this is equivalent to the fact that the graph gamma contains no copy of a subdivided complete graph on 4 vertices. So the JSJ decomposition in our setting is a canonical splitting of the group as a graph of groups over 2-ended edge groups. And I'll give examples during the talk if it's not familiar to you. So this class of right-angle Coxeter groups that we consider is very closely related to the class that it's attached to the graph of groups decomposition only along its boundary curves. I don't know if that's the terminology. I know. It's glued along its boundary curves. Right. Okay, so this class is very closely related to the class of geometric amalgams of free groups. This is a class of groups that was introduced by Lafont, and I'll denote this class by the letter G. And it can be defined topologically. We say a group G is a geometric amalgam of free groups if and only if G is the fundamental group of a two-dimensional hyperbolic P for piecewise manifold. In other words, X is the union of surfaces with boundary and negative Euler characteristic glued to each other along boundary curves. So that the resulting space X has no boundary components. So for example, we can take a surface with some genus and 3 boundary components, and the rule is that you have to glue at least two surfaces to each boundary curve. So this is an example of a two-dimensional piecewise manifold. And one nice feature of this class of groups is that the JSJ decomposition can be read immediately from the picture. In this example, the JSJ decomposition will have three two-ended vertex groups, one for each of the singular curves, and one maximal hanging Fuchsian vertex group for each of the surfaces you've glued on. So all of the shaded vertex groups are the fundamental group of some surface with boundary. So if G is a geometric amalgam of free groups, then G is delta hyperbolic, one-ended, two-dimensional in a natural sense, splits over a two-ended subgroup, and its JSJ decomposition contains only two-ended maximal hanging Fuchsian vertex groups. Within these classes of groups, the quasi-isometry classification is known. Oh, and sorry, I should have drawn. So I'll draw many examples later, but here's a simple graph that satisfies these properties. And you can draw many more. They're not that. All right, so the quasi-isometry classification was given by Malone for the class of geometric amalgams of free groups, was given by Dani and Thomas for this class of right-angled Coxeter groups, and it also follows from recent work of Cashin and Martin, which generalizes this result and recovers the theorem as a special case. So we know that if G and G prime are groups in the union of these two classes of groups, then G and G prime are quasi-isometric if and only if G and G prime have isomorphic JSJ trees. By JSJ tree, I mean the Basser tree of the JSJ decomposition. So in this example, the JSJ tree is a biregular tree with vertices of valence 3 and vertices of infinite valence. And what the theorem says is that if you build any two-dimensional hyperbolic piecewise manifold where surfaces meet each other with exactly 3 meeting at each singular curve, then the two groups are quasi-isometric. The proof of the theorem, one direction of the proof of the theorem follows from work of Bowditch. He constructs the JSJ decomposition using the topology of the visual boundary, the JSJ tree using the topology of the visual boundary of the group. So if two of these groups are quasi-isometric, since their boundaries are homomorphic, they have isomorphic JSJ trees. The other direction of the proof uses work of Berstock and Neumann on the bi-Lipschitz equivalence of Fatten trees, which give a model geometry for the pieces in the universal cover of such a space. In addition, what Malone does is, given two JSJ decomposition graphs, he can determine if the JSJ trees are isomorphic using an algorithm, and Dani and Thomas construct the JSJ decomposition from the defining graph of the right-angled Coxeter group. So again, you can determine if the groups are quasi-isometric. So we've seen that these two classes of groups are very similar. They have a similar description and a similar quasi-isometry classification. The difference is that the right-angle Coxeter groups are generated by torsion elements, while that's not true for geometric amalgams of free groups. And it's natural to ask if you can distinguish these classes of groups geometrically in the large-scale geometry. So we show that if W gamma is a right angle Coxeter group in the class W, then there exists a geometric amalgam of free groups so that W gamma is an index 16 subgroup of G. So that G is an index 16, sorry. So that G is an index 16 subgroup of gamma. Sorry. So in particular, every group in the class of right angle Coxeter groups is quasi-isometric to a geometric amalgam of free groups. And we prove the converse fails. So for example, the fundamental group of a hyperbolic piecewise manifold with three singular curves, which are glued in a cycle, and to each of the singular curves, a different number of surfaces with boundary are attached. The fundamental group of this complex is not quasi-isometric to any group generated by torsion elements.
Or you mean any group?
To any group generated by torsion elements. And the reason is that the JSJ decomposition graph of any group generated by torsion elements must be a tree. If there were a cycle in the graph, then the group would surject to the integers, which can't happen. So you can study what the JSJ tree of such a group must look like and prove that can't be isomorphic to the JSJ tree of this, which contains a cycle. So the class of geometric amalgams of free groups geometrically is strictly larger than this class of right-angle Coxeter groups. And part A, the proof is constructive and plays a role in our commensurability classification. So I'll give an example later. So for the rest of the talk, I'll describe what is the commensurability classification that we know. So we give a commensurability classification for the set of right-angle Coxeter groups in the class W whose JSJ graph has diameter less than or equal to 4. And similarly, the set of geometric amalgams of free groups whose JSJ graph is a tree of diameter less than or equal to 4. And this work extends previous work of Crisp and Pallavi for a subclass of the right-angle Coxeter groups with JSJ graph of diameter 2 and it extends work from my thesis for the class of surface group amalgams. It follows from our classification that within each quasi-isometry class, among these classes of groups, there are infinitely many abstract commensurability classes. So I'll start by describing what is the commensurability classification for the right angle Coxeter groups in this class with JSJ graph of diameter equal to 2. These are exactly the groups for which the graph gamma is what we call a generalized theta graph. So this graph is a theta graph with two vertices and 3 edges connecting them. A generalized theta graph has 2 distinguished vertices, some number of edges connecting them, and we require that each edge is divided into at least 3 additional edges. The right angle Coxeter group with defining graph gamma is the orbifold fundamental group of an orbicomplex built by gluing together orbifolds with boundary along their boundary curves. The right angle Coxeter group with defining graph a path of length 4 is the orbifold fundamental group of an orbifold with one non-reflective edge and 4 reflection edges that meet each other at right angles. So the orbicomplex will be built from 4 orbifolds with the number of reflection edges determined by the number of vertices along the path. So in this case, there will be 2 orbifolds with 4 reflection edges and 2 with 5. And what happens when they're glued together? The top reflection lines meet each other at right angles. So there's one reflection wall at the top, which corresponds to the top vertex of the defining graph. One reflection wall at the bottom of the complex, which corresponds to the lower vertex in the defining graph, and all of the other reflection walls correspond to the other vertices of the defining graph. So what is the JSJ decomposition of this group? It has one 200 vertex group, which is isomorphic to the infinite dihedral group, coming from the cut pair of vertices in the defining graph. And it has 4 maximal hanging Fuchsian vertex groups coming from the 4 orbifolds, and the vertex group is the right angle Coxeter group with defining graph a path of the appropriate length upon gluing. So the JSJ tree for this group will again be a biregular tree with vertices of valence 4 and vertices of infinite valence. So the quasi-isometry classification tells you that 2 such groups are quasi-isometric if and only if you've chosen the same number of paths to define your graph. To give the commensurability classification, we need to record more data, and we do that using what we call the Euler characteristic vector. Which I'll denote by V gamma. And it just records the orbifold Euler characteristic of the orbifolds you've glued together along the non-reflection edge. Listed in non-decreasing order, so it's unique. And you might guess this is a reasonable object to consider when studying commensurability classes because Euler characteristic is multiplicative under finite in sheeted covers. So we'll use this to describe the commensurability classes. And the notion of commensurability goes back to Euclid, I think, who said that two line segments, A and B, were commensurable. There exists a third line segment that contains an even number of copies of each of the earlier line segments, each of A and B. So in other words, A and B are commensurable if and only if they're rationally related. So you can extend this notion to vectors, where we say vectors V and V prime are commensurable if and only if there exist non-zero integers so that k times v is equal to k prime times v prime. In other words, the vectors are rational multiples of each other. And with this definition, we can state the commensurability classification. So if theta and theta prime are generalized theta graphs, the groups W theta and W theta prime are abstractly commensurable if and only if their Euler characteristic vectors are commensurable vectors. So it immediately follows that within each commensurability class, within each quasi-isometry class, there are infinitely many commensurability classes. And you can also compute the Euler characteristic easily from the number of vertices along each path, so it's easy to check if two such groups are commensurable. So to prove the theorem, one direction is constructive if the two groups have commensurable Euler characteristic vectors, we construct homeomorphic covers of the orbital complex I've drawn above. And I'll give one example. So if you started with the orbifold with 3 orbifolds with 5 edges glued together, one way to construct a cover is to just reflect over the top reflective edge. And you can do this as many times as you want, where the cover is locally given by reflections. And what you get is, again, an orbital complex, where these are now interior edges, and the Euler characteristic vector of the resulting thing is exactly the number of copies you've taken times the original Euler characteristic.
What are the links in the universal cover of the orbifold?
It will be the links. Either squares or like, let's see, I guess it's here. like a suspension of 3 points or k points.
Right, so you've got, okay, I think, yeah. So complete by parts like graphs, is it?
Yes.
Yeah.
Yes.
Yeah.
Yeah. Okay. Yeah, so using these covers, you would take k copies on one side and k prime copies on the other side, and they're homeomorphic by the Euler characteristic computation. Right. Okay, so what about the groups in this class with JSJ graphs of diameter equal to 4? These are exactly the right angle Coxeter groups whose defining graph is a cycle of generalized theta graphs. In other words, gamma is the union of some number of theta graphs with one or more edges along their distinguished vertices, so that each of the paths you take are subdivided into at least 3 edges, paths of length at least 3. So here's a specific example where there are 3 distinguished vertices, and each are connected by paths of length, by 2 paths of length either 3 or 5. Again, the right angle Coxeter group, W gamma, is the orbifold fundamental group of an orbicomplex built by gluing together reflection orbifolds, one for each path in your defining graph. So in this case, since there are 3 cycles of three generalized theta graph, the orbicomplex will have a non-reflective subspace, which is a tripod, and glued to pairs of its paths are orbifolds with either 5 or 7 sides, reflective sides. And you can't draw it on the board, but all of these angles are pi, so you have one orbifold with boundary and another, and you glue them together just along half of their boundary. As above, this is homeomorphic to the quotient of the Davis complex for the group, so it can be subdivided as a square complex. That's a more familiar geometry to you. Okay, so again, what is the JSJ decomposition of this group? It has one central hanging Fuchsian vertex group, which is generated by the 3 distinguished vertices in the JSJ decomposition, which gives you a virtually free subgroup. It will have 3 two-ended vertex groups, each isomorphic to the infinite dihedral group, which correspond to pairs of these cut vertices in the defining graph. And it will have maximal hanging Fuchsian leaves with fundamental group, the right angle Coxeter group with the defining graph, the path, which corresponds to these orbifolds you see in the orbicomplex. Oh. So what is the commensurability classification within this class of right-angled Coxeter groups? If gamma and gamma prime are cycles of generalized theta graphs, then the right-angled Coxeter groups W gamma and W gamma prime are abstractly commensurable if and only if either one of two conditions holds. First, the set of commensurability classes of theta graphs in W gamma is equal to the sets of commensurability classes of theta graphs in W gamma prime, which I'll say what I mean in a moment, and a natural ratio holds. So this is a bit cumbersome to write down, but what I mean is that you can define the cycle of generalized theta graphs by piecing together generalized theta graphs. So you look at the commensurability classes for each of these graphs, and the set from one side must match the set from the other side. And the ratio, you basically add up the Euler characteristics of the orbifolds in each commensurability class and compare it to the Euler characteristic of the maximal hanging Fuchsian group in the center of your JSJ decomposition. And that ratio must match on both sides. The second possibility is that there's one commensurability class of theta graphs in each of W gamma and W gamma prime, and again, a natural ratio holds. So in this case, this happens exactly if you have generalized theta graphs with the same number of vertices, or the same number of paths, and there's one commensurability class for each of the two groups. They don't have to match. And a simple situation is that you have exactly the same theta graph in each of your graphs in your cycle, and then your JSJ graph has a symmetry about the center vertex, in a sense. So these are exactly the groups that are commensurable to the right-angle Coxeter groups with JSJ graph of diameter 2. It's the second situation. So for the rest of the talk, I'll describe what goes into the proof of this theorem. And as before, one direction is to construct homeomorphic covering spaces. The construction is more involved in this case, so I won't give an example, but I'll describe the other direction of the proof. So in the other direction, we ask if the converse of this statement holds. That is, if you have two right-angle Coxeter groups and you know that they're abstractly commensurable, do you know that there are finite covers of their orbicomplexes which are homeomorphic? Then you can use topological methods to distinguish the commensurability classes. And to make that more precise, we'll use the notion of topological rigidity. So if X is a class of orbit spaces A class of orbit spaces X is topologically rigid if for all X and X prime in your class of spaces, X and X prime have isomorphic fundamental groups if and only if X and X prime are homeomorphic spaces. So it's a strong condition you can ask a class of spaces to satisfy, and why it's relevant if, in addition, for all spaces in your class, all finite covers of your chosen space are in the class of spaces X, then for any two spaces, X and X prime, in X, their fundamental groups are abstractly commensurable if and only if X and X prime have homeomorphic finite covers. So if these conditions are satisfied, you can pass from the algebraic notion of commensurability to a topological notion of commensurability. So an easy non-example is to take the set of graphs. Is not a topologically rigid class of spaces. Here are two graphs with the same fundamental group that are not homeomorphic. So this notion really has its roots in the setting of manifolds. For example, the Poincare conjecture says that the three-sphere is topologically rigid, which we know now to be true. And the result that's most relevant to us is the theorem of Lafont, which says that the set of two-dimensional hyperbolic piecewise manifolds is topologically rigid. So if you build two of those spaces out of lots of surfaces glued along their boundary curves, their fundamental groups are isomorphic if and only if the spaces you've built are homeomorphic. And we can ask if a similar thing holds for these orbital complexes, which are a quotient of the Davis complex, which is a natural space to study for these right-angle Coxeter groups. And it doesn't hold. So we show the set of finite covers of the orbital complex O above is not topologically rigid. And the reason is that the singular subspace is itself an orbital complex with underlying space a tripod and three orbifold points of order 2. And this is twofold covered by the theta graph, where the cover is just given by reflection. And the class of graphs is not topologically rigid. So you can expect the same to hold here. And indeed, you can find finite covers of the graph with the same fundamental group that are not homeomorphic. And the content of the theorem is to prove that, in this case, you can extend the cover to the Orba complex to get spaces with the same fundamental group that aren't homeomorphic. So if you want to study commensurability for these groups from a topological point of view, the quotient of the Davis complex is sort of the wrong object to pick. So what do? The solution is to thicken the singular subspace So for O, which is drawn above, we replace the red singular subspace with a surface with an orbifold with 3 reflection edges and 3 non-reflection edges, and glue on the orbifold as before. So now the singular subspace are one-dimensional orbifolds which are finally covered by curves. And to prove the theorem over there, we show that this complex has a degree 16 cover, which is a 2-dimensional hyperbolic piecewise manifold with 1 center surface and 3 pairs of boundary curves onto which surfaces with 2 boundary components are glued. So to obtain the commensurability conditions, we study finite covers of these spaces, and the idea is to consider what happens to sort of the center surface from both copies. And we show that basically it reduces to the case that the center pieces have homeomorphic images in the finite cover, or can be taken to be disjoint, and analyze those 2 situations, which give the 2 situations from the theorem. So to conclude, it would be very nice to understand the commensurability classes for a larger class of these groups, and very little is known for right-angle Coxeter group except for those which are virtually manifold groups. And I think like nothing is known in the relatively hyperbolic setting. So, thank you.
Plenty of time for questions. Daniel?
Is that theorem of Lafont's false if you drop hyperbolic?
Yeah, because you can have once annuli are glued together, you can move them around a lot.
Oh, okay.
So we glue a bunch of tori. Yeah, the proof is to use the structure of the visual boundary, and an isomorphism will give you a homeomorphism between the visual boundaries, which you can pull inside the space.
Do you have a class that you're going to work on next of Coxeter groups?
I think the very simple, relatively hyperbolic ones would be good to consider. So if you take theta graphs and allow edges of paths of length 2, we don't know what the commensurability classification is. So those are hyperbolic relative to flats or to free bicyclic, free times C.
We're going to have to finish early. Let's have 10 minutes of applause.